In section 4.3, part 1, we discussed scalar multiplication with a matrix. In 4.3, part 2, we're going to discuss matrix multiplication. We want to multiply two matrices together. To find element Cij of the product matrix A times B, two matrices multiplying together, multiply each element in the ith row of A by the corresponding jth column of B. Then we want to add that quantity together, and that will become that element. Let's take a look at an example. First, to perform matrix multiplication, multiply the elements of each row of the first matrix by the elements of each column of the second matrix and add the products. But we have a key issue that we have to make sure we have. The product of two matrices A and B exists only if the number of columns of A, and in this situation I have two columns, is equal to the number of rows in B. And here I have two rows. So that means I can find the product of these two matrices. The next slide will show the actual procedure to do this. Here is an example pictorially. So this is the two matrices from the previous slide. So we want to take the first row of A and multiply it by the column of B. So 2 times a negative 1 and negative 3 times 5. Then we want to add that quantity. And when we do, that goes back into element 1, 1 of my matrix. And then I want to do the same thing to get the second column. So I take my same row and multiply it times the second column. And that's going to give me 2 times 4 plus negative 3 times 3, which is a negative 1. And that gives me this element. Then I take my second row times the first column, and that becomes negative 11. And then again, my second row times my second column, which gives me a negative 2. And that is the solution. Let's take a look at another example. Remember, to multiplying matrices, I need to have the number of columns in matrix A, which here I have 2, equal the number of rows in matrix B. And again, I have 2. I also set up another pictorial example of this procedure. So let's follow through. Row 1 times column 1. And when I have that, that gives me 3 times 4 plus 2 times 0, which is 12. And that goes into element 1, 1. And then row 1 times column 2. 3 times a negative 1 plus 2 times 2. I add those products and I get 1. And that is row 1, element 2. And finally, I have the first row times the third column. I find the product and the sum of that, and that gives me 9. And that is row 1, element 3. Then I take the second row and multiply it times the first column. And that gives me 4. So that's going to give me element 2, 1. The bottom row times the middle column, or number 2, is going to give me 7. And that's element 2, 2. And finally, the bottom row times the third column is going to give me 13, and that is going to give me element 2, 3. So a set procedure of going across the row and down each successive column, and then going to the second row and going down each successive column, is a procedure that should be used to find the solution of multiplying matrices. As previously stated, when I multiply matrices, the number of columns in matrix A has to equal the number of rows in matrix B. But an outcome from that is the solution, or the product matrix, is going to equal the number of rows in matrix A, and that's going to be equal to the number of columns in matrix B. So here you can see I have these two equal, 2 columns, 2 rows. Therefore, I can find the product of these matrices. the product of those two matrices will be a 3 by 5. We can take a look at that on our previous example. Here, I have a 2 by 2. And I know this 2 by 2, its product will have a 2 by 3 matrix. And that's proven. 2 rows, 3 columns. And that worked out with my first one also. 2 by 2. Notice it's a 2 by 2. And my solution will be a 2 by 2. And that's proven again here, a 2 by 2 solution. As before with scalar multiplication, the properties of matrix multiplication exist. Closure, associative, distributive, multiplicative property of 0. Let's take a look at another example. I want to find the dimensions of each product, then determine the product. Here, I want to make sure I can multiply these together. Remember, the number of columns has to equal the number of rows. And since they are both 1, then I know that that's going to exist. But I know the outcome is going to be a 3 by 3 matrix. And we can prove that by finding the product. So the first row times the first column, it just happens to be one element in each. 2 times 3 is 6. The first row times the second column is going to give me a negative 4. The first row times the third column is going to give me a negative 6. The second row times the first column is a negative 9. The second row times the second column is 6. The second row times the third column is a positive 9. The third row times the first column is 15. The third row times the second column is a negative 10. And the third row times the third column is a negative 15. So as stated on the previous slide, our columns of matrix A must equal the rows in matrix B, which it did. Then the resultant matrix, or product matrix, will have a 3 from the first matrix and a 3 from the second matrix, rows by columns, a 3 by 3. Again, I want to find the dimensions of each product, then determine each product. Let's verify that we can multiply these two matrices together. Remember, matrix A has 3 columns. Matrix B has 3 rows. Since these two values match, I can find the product. The resultant of that product will be a 1 by 1, and that's determined by the number of rows in A and the number of columns in B. So the resultant will be a 1 by 1 matrix. The process to do that is going to take this row times this column. When I do, I'm going to have each element match up and multiply each element and then find its sum. So this is a 3 times 2, which is 6. A negative 2 times a negative 3 is a positive 6. I want to add those. And then a negative 3 times 5 is a negative 15. Again, we'll add that. Find their sum, which is going to give me a 1 by 1 matrix, and it's going to be a negative 3. 1 row, 1 column. Again, in this example, we want to find the dimensions of each product and then determine each product. Let's verify that we can find the product of these two matrices. We know that the columns of matrix A must match the rows of matrix B, and they do with a 2 by 2. Now we can determine what the outcome will be, because I know the number of rows in matrix A and the number of columns in matrix B determine the matrix size of the product. And my matrix size will be a 1 by 2. Let's determine the product. I'm going to take my first row times the first column and find the sum. Negative 2 times 0 is 0. 3 times 5 is 15. 15 plus 0 is 15. My row times the second column. Negative 2 times a negative 3 is 6. 3 times 2 is 6. 6 plus 6 is 12. And that is my 1 by 2 matrix. Again, we want to find the dimensions of each product and determine each product. Let's verify that we can find the product of these two matrices. Matrix A has 2 columns. Matrix B has 2 rows. Therefore, that verifies that we can find the product of these two matrices. Let's determine what the dimensions of the product will be. This has 3 rows, 2 columns. Therefore, my product will have 3 rows and 2 columns, or a 3 by 2 dimension. Let's begin by taking our first row and multiplying by our first column. That's going to be 0 times 0, which is 0, and 2 times A. So that will be 0 plus 2A. And when I combine those terms, that's going to give me 2A. Now our first row times our second column is going to give me 0 times C, which is 0, and 2 times B, which is 2B. Simplify gives me my second term, which is going to give me 2B. Let's start with our second row. First column, 1 times 0 is 0, 1 times A is A. That's going to be 0 plus A. When I simplify, that's just A. Our second row times our second column, 1 times C is C, plus 1 times B is B. And that will just be C plus B, because they're not like terms. And finally, our third row times our first column, negative 2 times 0 is 0, and 0 times A is 0. And that will simplify to just 0. My third row times my second column, negative 2 times C is a negative 2C, and 0 times B is 0. And when I simplify, that's going to be a negative 2C. And that is my product matrix. And of course, it is a 3 by 2. In this example, we want to determine whether each product is defined or undefined. In other words, we want to verify that the two matrices have the correct dimensions that we can actually multiply them together. Let's start with A times B. Matrix A has 2 columns, and B has 2 rows. Therefore, these match up, and we can verify that they are the correct dimensions, so therefore this product is defined. Number 2, B times C. B has 2 columns. C has 3 rows. These do not match up. Therefore, they have incorrect dimensions to be able to find their product. Therefore, this is undefined. Number 3, A times D. A, 2 columns. D, 2 rows. Therefore, these do match. Therefore, we can say that the products can be defined. Number 4, C times E. C has 1 column. E has 1 row. Therefore, the values match, and we can verify that we can find the product. Therefore, it is defined. Number 5, E times C. E is 3, and C is 3 rows. Therefore, the values match. Therefore, the product can be defined. Number 6, B, 2 columns. A, 3 rows. The values do not match. Therefore, the product is undefined. In this example, I need to find the value of x and y. To do that, I need to find the product of these two matrices, simplify the expressions, and set them equal to the corresponding element in this matrix. Let's begin by verifying that I can find the product by looking at the dimensions of both matrices. This has 2 columns. This has 2 rows. Therefore, that does verify that I can find the product. Let's begin by taking the first row times the first column. That gives me 3x, 2 times a negative 1, plus a negative 2, or minus 2. First row, second column, 6x. 2 times y is plus 2y. Second row, first column, negative 1 plus a negative 1 is a negative 2. Second row, second column, negative 2 plus y. And set that equal to its corresponding matrix, 7, 6, negative 2, and negative 8. Now, all I have to do is set each expression equal to its corresponding element. Let's begin with 3x minus 2 equals 7. Therefore, add 2, 3x equals 9, x will equal 3. I already have that negative 2 equals negative 2. That's good. Let's solve for y in that expression. So I'm going to have a negative 2 plus y equals a negative 8. That gives me, when I add 2 to both sides, y equals a negative 6. Finally, let's verify the result by setting this expression equal to that element. That gives me 6 times, I already found out what x is, which is 3, plus 2 times y, which I found to be a negative 6, and that should equal 6. Simplifying, 18 minus 12 equals 6, 6 equals 6, and that is true. Therefore, x is 3 and y is a negative 6. In my next example, I want to perform the indicated operations if they are defined. If an operation is not defined, label it undefined. In my first expression, I want to take matrix A minus matrix C. A is a 2 by 2, C is a 2 by 2. In addition and subtraction, they need to be the same dimensions, which they are. So that is defined. So when I do that, I'm going to set it up like this. Matrix A, 5, 6, 3, negative 2. Matrix C, 6, 2, 1, negative 1. And matrix B is 1, 2, 4, negative 1. Now what I need to do is to subtract, since they are in parentheses first. So I have to perform that operation first. 5 minus 6 is a negative 1. 6 minus 2 is 4. Negative 2 plus 1 is a negative 1. And 3 minus 1 is 2. Now I want to check for the dimensions again. 2 columns, 2 rows. I can perform that operation. And when I take the first row down the first column, negative 1, negative 4, I'm going to get a negative 5. First row, second column, negative 1 and times 2 is going to be a negative 2 plus 16, which is 14. Second row, first column, negative 1, negative 2, I get negative 3. Second row, second column, I get a negative 2 and 8, which is a positive 6. Same example. I want to perform the operation if they're defined. If not, label it undefined. Here, I want to multiply A times B times C. When I do that, I want to make sure I can multiply A times B first. That's 2 columns, 2 rows. Therefore, I can perform that operation. And I'm going to set it up this way. We'll see if that works out for B, but it should, since I know the indicated operation is a product. Therefore, I have a 2 by 2 as a resultant of that product of A times B, which I have a 2 by 2 here. So let's perform that operation. First row, first column, I have 5 and negative 6. I'm going to get a negative 1. First row, second column, I get 10 and 24, and that's going to give me 34. Second row, first column, negative 2 negative 3, I get a negative 5. Second row, second column, I get a negative 4 and 12, I get 8. Now again, I can check it, but that's a 2 columns by 2 rows. So again, it's defined. I can find the product. First row, first column, negative 6, negative 34, I get a negative 40. First row, second column, negative 2 and 34 is going to give me 32. Second row, first column, negative 30 and negative 8 is a negative 38. And second row, second column is a negative 10 and 8, which is a negative 2.